All right, good morning, everybody. So in the last lecture, we stopped on this slide here. So we were talking about inheritance. We were going to use inheritance to create a new kind of counter. So a stopping counter is a counter that stops counting when it hits its maximum value. So when it hits integer max value, it stops counting. If you try to advance the counter past max value, it doesn't do anything. It just sits there at max value. And so instead of creating a brand new class where we have our field to represent the count and we have a bunch of methods that manipulate the counter, we just took our existing counter class and built on top of it. So we used counter as a superclass and we extended stopping counter so that it becomes the subclass of counter. That's what the extends keyword is. There's no fields in the class. So there's no field that represents the count or the value of the counter. Because we used inheritance, we get the field that the superclass defines to store the count. Right? So we're not repeating the definition of the value field here. We do need a constructor though, or constructors. So our no argument constructor for stopping counter sets the value of the counter to 0. So one way to implement this constructor is to not write it this way. You could write it, in fact, the way you would normally write it. Right? So you can just write this value equals 0. Right? So it turns out in this example, this would work and it would be correct. Right? We have access to the value field from the counter class, which is way back here somewhere. Oh, here we go, right? Which we changed to protected. So our subclass can access the field directly by name. Right? So you could write this value equals 0 and away you go, everything would in fact be fine. However, what you should get used to writing is what was on the slide to begin with. So what you should get used to writing is this funny super round bracket, round bracket. And so what that means here is that we're calling the superclass constructor. Which one are we calling? We're calling the no argument constructor. Right? So remember, the no argument constructor is the counter constructor that sets the value to 0. Right? Okay, so on the first line of every constructor body, it turns out there's a bunch of rules. We didn't need the rules previously because they didn't matter for what we were doing previously. Now that we're talking about inheritance, though, it matters. So now you need to know about the rules for what to do on the first line of every constructor. Okay, so inside every constructor, the first line must be a call to another constructor. Right? Now, previously, we didn't do that, right? We just initialized the values of our fields, and away we went. Everything was fine. Right? So the reason why that was fine is because the compiler is actually sticking some code in for you. Right? So if you don't call a constructor on the first line of your constructor body, then the compiler inserts a call to the superclass no argument constructor for you. Right? So back here, right, if we don't put in super and we write this value equals 0, the compiler sticks in the call to the superclass constructor for us anyway. And similarly, when we made any other class in the course so far, right, the compiler was inserting a call to the object constructor for us. Okay. Question? Yes? That's right. You can't do that anymore. So you can't check for the, unless you're willing to accept the call to the superclass no argument constructor, right, you can't check for any preconditions before you call the superclass constructor. It's not allowed. You have to check it after the call to the superclass constructor. Yeah, it's strange, but that's the way it works. I'll explain, this lecture will explain why that's the way it works in Java. Right? All right, so if the superclass no argument constructor doesn't exist, or if it's private, then your class will not compile. Right? Okay, so rule number 2. the only place you can call a constructor from inside a constructor is on the first line, right? So by that I mean that the only place you can use this round brackets something or super round brackets something inside a constructor is on the first line, right? So that first line must be a call to another constructor, and that's the only place you can call another constructor. Now, that's not to say that somewhere you can, so you can, so that's not to say you can't call another constructor using new, right? So, trying to come up with an example here that actually makes sense. Okay, so this is silly, but okay. All right, so you can call another constructor if you use new, right? So you are allowed to make new objects inside your constructor. That's fine, right? What the rule is saying is that you cannot use the keyword super or the keyword this to call a constructor except on the first line, right? So for example, if you wanted to, you could go ahead and make a new list or something here, right? We've been doing that in the course anyway, right? Anytime you have a field that's of reference type, often we're making a new object of that type. Right? Okay, finally, the third rule. If you're in a subclass, at some point you must call the superclass constructor during the initialization of your object. So typically what you do is you call a superclass constructor on the first line, and that takes care of all three requirements right here. All right, so if you're wondering why these rules exist, we'll get to that in a few minutes. Right? So I'll explain exactly why this happens shortly. I just want to finish off this stopping counter example first. All right, so if you want to add other constructors, go ahead and add other constructors. Right? So for example, you might want to add a constructor that initializes the counter to some specified non-negative value. Right? So initialize a stopping counter so that its starting value is 10. For example. Okay, no problem. Stick in a constructor, right? Stick in your starting value here, right? And now what goes here? Well, this is a constructor, so you have to call a constructor on the first line. All right. Now, the rule is you have to call a constructor. You don't have to call a superclass constructor on the first line. You can chain if you want to. So you can still use this to call another constructor inside the same class. Where did I do this? This 0. Ah, yes, right. All right, so in the constructor that we're currently implementing, I can call the superclass constructor. Right? So in counter, we added a constructor that takes in the starting value of the counter. So I can call that constructor here. Right? And that satisfies rules 1, 2, and 3. Right? First line of the constructor is a call to another constructor. Right? Nowhere else in the constructor do we call another constructor, and we call a superclass constructor during the initialization of our counter. Right? You can go back and change the other, our no argument constructor to chain to our newly created constructor. Right? So instead of writing super round bracket, right, you can now write this and 0, which chains to here, which calls a superclass constructor. Right? So this also satisfies all three requirements. Right? This is a funny example because you can write these constructors in so many different ways. Right? So this uses chaining. You don't have to use chaining if you don't want to. Right? You could call the superclass constructor that takes in a starting value of 0. That's also fine. Right? As we saw earlier, you could just call the superclass constructor that takes in no arguments, and that sets the value to 0. You cannot do this. Right? Don't do that. Right? What does that do? That calls the stopping counter no argument constructor. So this is an infinitely recursive constructor call. Right? So don't do that. Right? You can write this value equals 0. That's fine. Right? What does that do? Well, the compiler silently inserts super for you, right? And then sets the value to 0. So that's fine. Somewhat surprisingly, this is also fine. Right. Why is this fine? So if your constructor body is empty, right, what happens? Well, Java inserts the call to the superclass constructor for you, which sets the value of the counter to 0. So in this case, that's also fine. Right. Down here, you can write this constructor in many different ways as well. So let me stick this back to the way we had it before. Sorry. So I'm going to use chaining in this example, this, 0 like that. Down here, right, so I can call the constructor that sets the value, the superclass constructor that sets the value of the counter. Right? You don't have to call that constructor. You have to call a constructor. So I could call the superclass no argument constructor and then set this value to value myself. Like that. Right? That's not quite correct, right? It's not correct because we're not validating the incoming value, right? The superclass constructor that takes in a value validates the value, so make sure it's not not negative, sorry. Here you would have to validate the value as well, right? But this also works. Similarly, that also works, assuming you validate value first, right? Why does that work? Because the compiler inserts a call to the no argument constructor for you here. Right? So it turns out there's lots of different ways you can write these constructors and still be correct. But what you have to what you have to remember in the back of your mind is that you do need to call the superclass constructors at some point. So, at least for the purposes of this course, the best practice is to insert the call to the appropriate superclass constructor on the first line and not worry about it. Yes?
Why does it work in the way that when we can't write this parenthesis because it refers to the stopping counter object, but we can do the stop value and then change the value for the counter object?
Sorry, repeat that question.
You said we can't use this parenthesis, right?
Up here you can't do that. So you can't write that. This doesn't, so that is a call to the stopping counter no argument constructor, which is the constructor that you're currently in.
So here this refers to the object of stopping counter.
No, that's the problem with, that's one of the issues with the use of the keyword this. When you use it as a name of the constructor, right, it refers to which class you're calling the constructor on, right? So this round bracket means call the no argument constructor in this class. So that calls stopping counter round bracket, which calls itself, which calls itself, which calls itself, which calls itself, and never stops. This dot value means something else. This dot value means change the field called value belonging to the object that was just created. It means two different things. Yes, it means two different things. Yes. When you're using it to call a constructor, it means call a constructor in this class. When you're using it to access a method or a field, it means access the field or method belonging to this object.
What if I call this
You can't do it. You're not allowed. A method can't invoke a constructor using this. Yeah, only constructors can do it. Yeah. What was this for? Like that. Okay, there we go. Okay, any other questions? All right, so what the heck do these rules exist for? Right, and so the answer is because of the way that Java implements subclassing. All right, so what exactly is a subclass object? So in other words, what exactly is a stopping counter? Right, so it's not just a counter that has some extra fields and maybe some extra methods, right? So it does more than just copy the stuff from the superclass, right? What actually happens is your subclass object contains an object of the parent class. So in other words, every stopping counter inside of it has a counter object. Right? Now, if you have an object, so if a stopping counter has a counter object, that counter object needs to be initialized, right? You have to make the counter object somehow. Right? So that counter object needs to be constructed just like any other object, right? And so the mechanism that Java uses to perform the construction of the superclass subobject is called the superclass constructor, right? So why is the constructor call to the superclass needed, right? Because a stopping counter has a counter inside of it, right? The counter part of stopping counter needs to be constructed. So we have to call this counter constructor somewhere, right? Why do we have to call it on the first line? So here's the reason why. Oh, sorry, this example is, if you're using the slides, be careful with this, there's a typo. It's a very misleading typo too, because the typo, it won't compile. That's what it should read. Okay, so I'm going to make a new stopping counter with initial value 1. Right. So what happens when you run this line of code? Right. Well, there's a call to new. Right. And so remember what new does. Right. New makes an object. Right. So it allocates memory for an object. So in this case, it allocates memory for a stopping counter object. So that's my big red box here. Right. New then calls the stopping counter constructor. Right? So our stopping counter constructor starts to run. Right? The counterpart of the stopping counter has to be created. So the very first thing we do is call the counter constructor. Right? The first line of a constructor body must be a call to another constructor. The first line of our stopping counter constructor calls the counter constructor. Right? And that causes the counter object to be created and initialized. Now, what does the counter constructor do? Right? So the counter constructor starts to run, right? The counter constructor, its very first line looks like this value equals 0. But you have to remember, it's actually a call to the object constructor, right? Because every class in Java inherits from object. So the counter constructor actually calls the object no argument constructor to create the object part of a counter. Right? I don't know what the object constructor does. It does something, right? And then it finishes running. So the object part of our stopping counter is now constructed. Right? That means that the counter part of our stopping counter, we can now finish initializing it. Right? So after the call to after the call to the object constructor, the next line is this value equals 1, right? Because we're going to set the value to that. Well, the next line is check the value of 1, make sure it's not 0, make sure it's not negative, and then set the value to 1. So now, inside the counter object, we can set the value of the counter to 1. Right? And that finishes the counter constructor. Right? Finally, the stopping counter constructor can finish running. Whoops, sorry. Right? The stopping counter constructor doesn't do anything else, so there's no other code after the call to the counter constructor, and so it's now finished running. Right? So the reason Java does this, so the objects are built from the inside out. Right? The object part of the stopping counter gets constructed first, then the counterpart of the constructor of the object then the counterpart of the stopping counter gets constructed. Finally, the stopping counterpart of the stopping counter object gets constructed. The reason why the objects get built from the inside out is because the stopping counter constructor might need to do something with the value. Right? If the value isn't set here, when the stopping counter constructor is running, funny things could happen. Right? So for example, where'd we go? Back here. Oh, sorry. Okay, Oh, sorry, not that. If this dot value. Okay, so imagine that the counter constructor that takes in a value doesn't do any validation. Right? So it just sets the value to whatever you pass in. Right? Now our stopping counter has to do the validation. Right? So if the stopping counter tries to access this dot value, well, it's going to access this dot value and check if it's less than 0. If it is, there's a problem. Right? We initialize this counter to a negative value, that's no good, so throw an exception. If objects weren't built from the inside out, so in other words, if the counterpart of stopping counter wasn't constructed first, this dot value isn't set at this point in the code, right? And so if it's not set, it turns out that Java sets all primitive values to 0, right? And so this will never, this test here will never throw an exception, right? So Java forces you to make sure objects are constructed from the inside out, right? The counter part of the class might need some field from object. It doesn't, but it might, right? The stopping counter part of the object might need to use the value, right? So the objects have to be built from the inside out, right? And that's the reason why you have to call the constructor. That's why every constructor needs to call its superclass constructor on the first line. Right? It's to force this inside-out construction of the object. Okay, we're almost done implementing stopping counter, right? All we have to do now is override advance. Right? So for advance, it's easy. Right? If the value of your counter is not max value, add 1. If it's max value, don't do anything, and away you go. Right? You don't have to re-implement value, you don't re-implement equals, you don't re-implement hash code, you don't re-implement toString. Right? All of those methods do exactly what they need to do for a stopping counter. Right? So there's no need to re-implement them again. Right? And your class is now done. Right? Okay, another example using counter. So instead of stopping, suppose you want to indicate that there's an error. So when you hit integer max value and you try to go past it, you throw an exception. Turns out this is not a great idea, but we're going to do it anyway. Right? So you do the exact same thing. Right? You make a class. In this case, it's called throwing counter. Right? You extend the counter class. Again, no fields. Right? I don't need a value field for the counter, for the throwing counter, because counter already has a value field that we can use. You need some constructors. You never, because classes don't inherit constructors. So the no argument throwing counter constructor simply calls the counter constructor that takes in the value 0. Right? The throwing counter constructor that takes in a value simply calls the superclass constructor that takes in a value. Right? Superclass constructor does all of the validation for us. Right? So we don't have to check the value here ourselves. The superclass constructor is going to check it for us. Okay, all that's left to do is implement advance. Right? So if the value of the counter is not max value, go ahead and add 1. Right? If it is max value, we're going to throw an exception in this case. So in this case, we throw a runtime exception. You could pick a different exception if you wanted to. Right? And that's it. Right? All right. So the mechanics of inheritance are relatively straightforward. Right? Change your, in your class header, use the keyword extends, right, and say what class you're inheriting from. Ask, do I need any new fields, right? So you get whatever protected, every non-private field from the superclass, you get a copy of that field. You don't duplicate them. Right? If you need new fields, go ahead and add them. Right? Now add your constructors. Right? If you have new fields, your constructors will set the value for your new fields. If you don't have any new fields, well, no matter what, right, whether you have new fields or not, make sure to call a superclass constructor on the first line of the constructor body. It doesn't matter which one you call, right? Call the one that's most appropriate. After this call to the constructor, to the superclass constructor, now initialize whatever fields you've added to the class, right? Do whatever other work you need to do in your constructor. Look at the methods that you need to redefine, right? So here we want to redefine advance, so you override the method advance, right? Again, inside the method, you get access to whatever fields, whatever non-private fields the superclass has. You can also, of course, access whatever fields you've added, whatever new fields you've also added. Right. All right, so the mechanics of inheritance, not terribly difficult, right? There's a few things you have to remember, in particular, what you have to do in a constructor. All right, so the question is should we have used inheritance in this example? Right? So when you're using inheritance, often there's an alternative to doing so. And so in this case, there is an alternative to doing so. So all of the counters that we've implemented, they only differ on one thing, right? The only difference is what happens when the counter is advanced past its maximum value, right? So to implement the different behaviors, we chose to override advance, right? We chose to use inheritance and then override advance, right? So there is a different approach here that you could take, right? So the other approach that you could take here is you can create an entire new class that describes the behavior of what happens when a counter is advanced past its maximum value, right? You can then use composition to hold an instance of that class inside your counter, right? So in other words, what you can do is you can create a class that has its own advance method, right? That advance method takes in a value and it gives you back the next value to go to, right? Now your counter simply asks its object that knows how to count, what's the next value, right? And so that would be a different way to solve this particular problem. But that's, I think that's a bit of an advanced topic for this course. All right, so we're now on to deck 24. And I think deck 24 starts out with, by repeating some slides from the previous lecture. Okay, so we've seen this before, still wrong. Nope. Okay, what about equals? So a few weeks ago when we learned about equals, we implemented equals using getClass. There is a second version of equals. The second version of equals is what you should consider using if you are trying to implement equals for classes that are related by inheritance, right? Okay, so in counter, we've already implemented equals, right? We've used the getClass version of equals to test whether or not two objects are both counters, right? Now remember what getClass returns. GetClass returns some object that corresponds to the class of the that corresponds to the object's class, right? So inside counter, this getClass is counter, right? OBJ getClass is whatever class of the object you passed in, right? So if we pass in a stopping counter, OBJ getClass is stopping counter, right? Counter is not equal to stopping counter, therefore this always returns false. So if we use a getClass-based version of equals in counter, I can't compare a counter to a stopping counter, right? Well, I can, but I always get back false, right? So a counter whose value is 5 and a stopping counter whose value is 5, they now compare as being false. They are not equal, right? And that might not be what you want in this particular case, right? You might want to be able to compare all types of counters simply by looking at their value. If that's what you want to do, you can't use a getClass-based equals in counter, right? So here, if you make two counters, C1 and C2, so on the right-hand, it's the right-hand side that matters here. So I make a new counter and a new counter, and I ask, are they equal? This is going to be true. Both objects are counters, and both values are 0, right? Now, if you use stopping counter, you still get back true, right? So remember, stopping counter inherits equals from counter. So stopping counter inherits a version of equals that looks like this, right? If I make two stopping counters, C3 and C4, they're both stopping counters. Then inside equals get class, this get class is stopping counter, obj get class is stopping counter. They're equal, so we don't return false. Right? On the next line, obj is a stopping counter. Right? Can I convert that to a counter, or can I cast it to a counter? The answer is yes, you can. Right? So this cast works even if obj is a subclass of counter. Why? Because it turns out that a stopping counter is a counter. Right? That's what inheritance means. Remember, inheritance models the is-a relationship. Right? So every stopping counter is also a counter, right? Which means you can cast a stopping counter to a counter object. Right? And now you can go and look at the values of the two counters. If they're equal, equals will return true. Right? So this also prints true. The problem is when you use a counter and a stopping counter object and try to compare them. Right? This now returns false. Right? The class of C1 is counter. The class of C2 is stopping counter. Right? So those two classes are different. Equal says false. Right? If you make a stopping counter and a throwing counter, right? C3 is a stopping counter. C4 is a throwing counter. The classes are different. Equals returns false. Right? So in some, not all, but in some inheritance hierarchies, you might want to compare objects of different types. Right? So for example, it doesn't matter what kind of counter you have. If their values are equal, you might want to say the two counters are equal. Right? If that's what you want to do, then you have to use what's called an instance of version of equals in the superclass. Right? So in counter. Right? What is the instance of based version of, yes, is this right? Yes, this is correct. Okay. So what does the instance of version of equals looks like? Well, it looks like this. Right? So it's still equals, right? Which means all of the requirements that equals has, you must satisfy using instance of instead. Right? So an object is always equal to itself. Right? So if this equals obj, you called equals with the same objects, right? You can return true right away. Right? Okay. Now in the get class version of equals, we check obj for null. Right? The instance of version, you don't have to do that because the instance of operator will check that for you. Right? And so right there is an example of using the instance of operator. Right? So on the left-hand side, you can pass in a reference variable. So here I'm going to pass in obj. Right? On the right-hand side, you can specify a type. Right? So here I'm going to specify counter. Right? So what instance of does is it tests, is the type of obj an instance of counter? Instance of means, is it a counter or any subclass of counter? Right? So if obj is a stopping counter or a throwing counter or a regular counter, obj instance of is true. Right? And so you skip down to the cast down here. Right? If obj is not a subclass of counter, or if obj is not a counter, then obj instance of counter is false. Right? And we immediately return false. Right? So instance of right there returns true if obj is from a class that has counter as one of its ancestors, right? Or if it's counter itself. And so that's the only difference, right? You don't have to check for null, and you replace get class with that instead. Okay, so now what happens? C1 and C2, they're both counters, right? So back here, C1 is this, C2 is obj, right? Is a counter an instance of a counter? The answer is yes. So this is true, right? And you go down to here. Right? Stopping counter and stopping counter, right? So inside equals, this will be a stopping counter, and obj is also a stopping counter, right? So is a stopping counter a subclass of counter? The answer is yes. So all that, so this is true, you jump down to here. Back here, counter, stopping counter, right? So again, inside equals, C2 is a stopping counter. obj is a stopping counter. So is a stopping counter a counter? The answer is yes. Right. In here, C4 is a throwing counter. So inside equals obj is a throwing counter. Right. Is a throwing counter an instance of counter, or is a throwing counter a subclass of counter? The answer is yes. So again, the condition here is false, and you jump down to the rest of the method here. Right? All right. So there's something new there that we haven't talked about yet. Right? And so the something new part is, so if you have an object in Java, how many types does it actually have? Right? So unless you have a big O object, all objects in Java have more than one type. Right? So an object's types include its own class type. Right? So if you have a stopping counter, then it's a stopping counter. Right? It also includes all of its ancestor class types. Right? So a stopping counter is a counter. So counter is one of the types that a stopping counter has. Right? And it's also an object. So a stopping counter is also an object. So stopping counter has 3 types. It actually has more. Right? You also get all of the interface types. And this includes the interfaces that the superclass is implemented. So we implemented comparable for counter. And so that means a stopping counter is also a comparable. Right? So that's one of its types as well. So here's our point 2 class. Right? Remember, in point 2, we implemented comparable, so we implemented an interface. Right? We didn't say it, but point 2 does extend object. Right? So point 2 has 3 types. Right? Point 2 itself, object, and comparable point 2. Right? So those are all the types that a point 2 object has. Right? There's stopping counter. Right? Stopping counter extends counter, which implements comparable. So stopping counter has 4 types. Right? It's a stopping counter, it's also a counter, it's also an object, and it's also a comparable. Here's string. Right? So string extends object, so one of the types of string is string. One of its types is object. It implements 3 interfaces, so it's also a serializable, a comparable, and a car sequence. Right? String has 5 types. So when you read or listen to somebody talk about inheritance, you'll often come across the term polymorphism. Right? So the dictionary definition of polymorphism is the condition of occurring in several different forms. Right? What this means in Java is an object has many different types. Right? So Java has what's called subtype polymorphism. Right? Every object has more than one type, except for big O object itself. Right? Subtypes are substitutable for their ancestor types. Right? So in other words, a stopping counter is substitutable for a counter. It's also substitutable for an object. So if there's a method that takes in an object, I can safely pass it a stopping counter. If there's a method that takes in a comparable counter, I can pass in a stopping counter. Right? Comparable counter is one of the types of stopping counter. So this subtype polymorphism in Java is made possible because the type of an object includes the type of all of its ancestor classes and all of the interfaces that it implements. Right. All right, so there was also something funny back here in the code that I showed you here. Right. So here we made a new counter, we made a new stopping counter. Right. But I'm storing that stopping counter in a counter variable. Right. Similarly down here, I'm storing a stopping counter in a counter variable here, and I'm storing a throwing counter in a counter variable here. So when you define a variable, you have to say what the type of the variable is. Right? So counter C says that C refers to a counter object. Right? We say that the declared type of C is counter. Right? So in other words, when you declare the variable, whatever type you say C has, that's its declared type. Right? Or the other way to think about this is the type on the left-hand side is its declared type. Right? What can you do with C? Right? So in Java, you can store the value null in C, right? Null means no object. Any reference variable can store the value null. Right? We know that I can store a reference to a counter object, right? So we can write counter C equals new counter. Right? But you can also store anything that's anything that is substitutable for a counter. Right? So for any class that is a subtype of counter, we can store a reference to that object there as well. So I can write counter C equals new stopping counter. Stopping counter is a counter, right? I can store a reference to a stopping counter in a counter variable. Why is the declared type important, right? The declared type determines what you can do with the variable, right? So here, I've got obj, right? And I'm going to store an array list in obj. Right? OBJ, its declared type is object. Right? I can store an array list in in OBJ. I can store any reference type in a variable of type object. Right? Because everything is substitutable for object. Right? So I can store a list in OBJ. Right? Now, I've told the compiler, hey, OBJ is a big O object. So what does the compiler do when you try to call a method using OBJ? Right? It says, right, so here I'm calling toString. So the compiler says, is there a method called toString in object? If the answer is yes, the method call is valid. If the answer is no, it's not valid. Right? So object says that there is a toString method, therefore that line of code is fine. So the problem that programmers new to object-oriented programming languages get into is they say, hey, I've got an array list, right? I've stored that in OBJ, right? I should be able to call an array list method using OBJ, right? So they write obj.add, and the compiler says that's not right, right? Why does the compiler say that's not right? What is the declared type of OBJ? Well, it's object. Does object have an add method? The answer is no. Object does not have an add method. So this is not legal in Java. Here's an example using set, which we haven't really talked about yet. Right? Set's a lot like a list, though, except that it guarantees the elements are unique. So it has an add method. Right? So tree set is a special kind of set. So set's actually the interface for all sets. Tree set is a particular kind of set. So it's the set that stores stuff in sorted order. Right? So can I store a tree set object in a set variable? The answer is yes. Right? One of the types of tree set is set, right? Because set's the interface that tree set implements. Right? Can I call add using T? The answer is yes. The set interface says that the add method exists. Right? Now tree set, it's the set that keeps things in sorted order. So it has methods like first and last and things like that, right? Things that refer to some sort of ordering of the elements. Right? So if you try to call the first method with T, the compiler complains. Right? It says set does not have a first method. Right? Tree set does, but you told me T is a set. Right? You didn't say that T is a tree set, so this doesn't work. Right? Okay. T add hello, T dot first. So this is, sorted set is what's called a sub-interface to set, right? So it inherits from the set interface. Sorted set has a first method, so this is legal. Okay, so that's the declared type, right? So remember, the declared type determines what can you do with the variable. Right? The runtime type is the thing on the right-hand side of the equal sign. So when you store a value or you assign a value in a variable, right, the right-hand side on the equal sign, that type is what's called the runtime type or the actual type. Right? So when you say counter C, you're saying C, its declared type is counter. When you store something in it, in this case we're storing a stopping counter, the runtime type of C is a stopping counter. Right? So runtime type or actual type. The runtime type determines what version of a non-static method is called when you use that variable. Right? So here I've got big O object, right? OBJ. Right? So the declared type of OBJ is big O object. Right? The actual type of OBJ, though, is a counter. Right? So in fact, OBJ does refer to a counter object. Right? When I use OBJ to call toString, right, this is when the runtime type matters. Right? So toString is a non-static method. So we get the runtime type version of toString. So we get the counter version of toString here. Right? So in other words, when I ask OBJ for its string representation, I get whatever toString for counter returns. Right? I don't get the big O object version of toString. So here's a print method. Right? It takes in any argument, and the declared type of the argument is big O object. Right? So this method will take in any object reference. Right? Internally, it uses obj.toString. Right? That's legal. Right? Big O object has a toString method, so that's fine. Right? What version of toString do you get? You get the runtime type of whatever obj happens to be. Right? So if S is a string, then when you call print, you get the string version of toString. Right? If T is a list, when you call print, you get the list version of toString. If if O is a date, when you call print, you get the date version of toString. Right? You don't get the object version of toString. It's the runtime type that determines which version of toString you get. All right, so the compiler can't tell. So when you look at this code here, right, this is all that the compiler sees. Right? So the compiler sees there's a call to toString using obj. The compiler says, does object have a toString method? The answer is yes. Right? And so the compiler is perfectly happy with this code. It does its work, and away you go. Right? What the compiler never sees is what is the actual runtime type of the object that was used to call the method. Right? So the compiler can't determine which version of toString gets called in the method print. Right? But the printer class still compiles without any issues. The actual version of toString that gets called, no one knows what that is until you run your program. Right? So when you run the program, it's the Java virtual machine that determines which version of toString needs to run. Right? So using the runtime type to determine which version of a method to call is called dynamic dispatch or late binding. Right? Dynamic meaning at runtime. Right? Dispatch meaning what version of the method do I have to call? Right? Late binding means the exact same thing. Right? Early means at compile time. Late means at runtime. Binding means what version of the method to call. Right? So all of this means the version of the method that gets called isn't determined until you run your program. Right? All of this works because of polymorphism. Right? This method works because reference types in Java have more than one type. Right? One of those types happens to always be object. Right? So that example there, it looks dead simple. Right? There's nothing here. Right? All there is a call to toString and a call to print line. But that example right there illustrates the power of polymorphism. Right? The fact that objects have more than one type means a programmer can write a method using the interface of an ancestor type. So using the methods of an ancestor type or the methods of an interface. Right? And that method works for objects of any descendant type. Right? So this print method works for any object in Java. Right? It doesn't matter what kind of object you pass in, this thing always works. Right? This works for objects, for classes that haven't even been created yet. Right? So if you went home right now, created your own class, called this method, it would work. Right? Someone implemented this method having no idea what actual type of object you're going to pass into it, and yet it still works. Right? And so that is the power of polymorphism. Right? You can write code for stuff that hasn't even been created yet, and it will still run, as long as you implement inheritance correctly. Right? So if you look in the class Java util collections, you'll find a bunch of methods that take in lists and sets. It doesn't matter what kind of list or set, it works, right? You can pass it in a linked list, you can pass it in an array list, you can pass it in some kind of set. The method does exactly what the method says it'll do, right? You can make your own list, pass it to one of these methods. Assuming you implemented your list correctly, the method will do exactly what it says it'll do. All right, so we're at the end of the lecture time. I guess we should stop there.